Okay, this is going to be a very short, brief review on some points in mechanics that are going to be necessary really for our study in electricity and magnetism. And so what I'd like to do first off is just really just go over very briefly some basic concepts of the area in mechanics that are going to be applying. We start off, if you recall, when we were doing accelerated physics last year with this notion of motion. Most things, if not everything, in the universe is in motion. And so, what that means basically is that if an object, some object denoted by x here, is at some initial position in space. So here it sits, little x right here in space, and at some later point in time, it could be a short period of time, it could be a very long period in time, but the object changes its position. So now it winds up here at some final position, at some final point in time. We say that the object undergone a displacement. So it went from initial to final, and this is going to be our displacement vector here. So we say it was displaced. Come on, work. There's the displacement. It's a vector quantity, so it's showing you where it started, right here, and where it finished. The length of the displacement vector will indicate the distance. So the length of the vector tells us the distance, and the direction is going to tell us exactly the angle, or in which direction, where the arrow of the vector is pointing is going to show us in which direction it was displaced. Now, when we're talking about objects that moving from one point to another point, what we're interested in is how quickly is that done. In other words, for an object to go from here to here, does it take a matter of seconds, hours, days, years, light years, and so forth? So we're interested in the displacement of an object, but how long it takes that displacement to occur. The displacement denoted by this delta, let's say, for example, we're going to talk about here in this example just a one-dimensional displacement. So it's only got one dimension, let's say the x-axis. So it moves, remember our x-axis over here. An object might be here at some initial position, and it might wind up here a little bit later. And if you want to know the displacement from this point to that point, that vector over there, what you have to say is this change in x is always going to be the final minus the initial position over the time, which is some change in time, or some delta t, some how long it takes. In other words, to go from here to here is delta t. So this is my initial time, designated by t0 or t0, and this is my final time. Then my change in time is t final minus t initial. That's my change. That delta means change. And we call this velocity. Okay, so that's the concept of velocity. It's a displacement. Something's moving. It's going from one position to a new position. Velocity is a vector. It has both magnitude and direction. And what it is a rate, because this time factor is in here now. It's a rate. How quickly is this position changing? The next concept that flows logically is the concept of acceleration. So if velocity is the displacement over time, or the rate of displacement, rate of change of displacement. Then acceleration is the rate of change of velocity. In other words, if something is going and moving and changing its displacement more rapidly, and that rate is increasing or decreasing, you have an acceleration. So we might think of something as going faster or slower or changing its direction, because a velocity is a vector quantity, so it could change in a couple of ways. Velocity, it can either increase, so let's say it can go up, increase, it can go down. In either case, whether the velocity increases or decreases, it changes, so you have this idea of changing the velocity. It may stay at the same magnitude, 5 miles an hour. It may stay steady. But if the object is changing direction, it's going in this direction 1 minute, and then the next minute you look and it's going in this direction, then it undergone an acceleration. Now, when something accelerates, it's said to have some net force applied to it. So that's the next concept that I want to show you. And let's see, forgot how to do this. Oh, there we go. Well, nice, doing this quickly. All right, so if there's a net force on some object, then that object's going to experience an acceleration, and Newton's second law says the mass of the object times its acceleration will equal its net force on it. So you could think of an object. Say we have an object here, some rock, and it's still, so let's say it's at rest, and this is at time t0, and then you look at it again later at some time t final, some later point in time, and you observe the rock moving with a velocity equal to, let's say, 3 meters per second. Then there was a change in velocity, wasn't there? Here the velocity was 0. Here it's 3. So there was an acceleration, wasn't there? There was a change in velocity in this change in time. The velocity is 3 meters per second, the final minus the initial, over t final minus t initial. That is your acceleration. Let's say it's your average acceleration. Now, what caused this stone or this rock to move? Ultimately, there had to be some force. Something had to push it. Some force, which I'm going to call force net, had to be applied to the rock to change its velocity from 0 to some final value, and hence accelerate it. And so this is what we're interested in, Newton's second law, where the net force acting on the object is going to produce an acceleration. If I just have an object sitting here like this, I have a force here, F1, in this direction, and another force here, F2, in this direction. If the magnitude of force F1 equals the magnitude, and I'll show it with an absolute value sign, then the force net is 0. Say that because they're in opposite directions. As vectors, they cancel one another out, and there's no net force. So the acceleration is 0, and as you might expect, the object remains at rest. Okay, so that's the concept of net force as it ties into mass times acceleration. Now there's one other concept I want to introduce, and we'll do maybe one other little short video after this one and we'll be finished, and that's the concept of work. So what is work? Work in a scientific sense is when you have a force that's applied to some object. Here's my object. Let's say this object is on the floor. It's not so straight, I know, but you have some force that's being applied, F, and the object moves from some initial position to some final position. So there was this idea of a displacement, okay, from this point to this point. There's my displacement, and we have some force being applied in order to make that happen. Let's say this is my net force. So my net work is going to be the net force times the displacement, which I'm just going to call D for displacement right now. Now, that assumes that the force as a vector is in the exact same direction as the displacement. This would be my displacement vector from initial heading this way to final. If both are parallel and in the same direction, then the net work done is this force times distance. But what if they're not parallel to each other? That I'm going to talk about in the next video.